Hello everyone, welcome to today's tutorial, and in this tutorial we're going to talk about the dihedral group. So what is the dihedral group? As I've mentioned in my earlier videos, the dihedral group is a group that shows you the rotations of a regular polygon, the rigid rotations of a regular polygon. So we can combine both the reflections and the rotations of a triangle to give D3, which is the dihedral group for an equilateral triangle. So if you combine those, you would have D3 equal R. Remember, what is R? R is a rotation of 120 degrees anticlockwise, R2 240 degrees anticlockwise, R3 360 degrees anticlockwise, which will give you the identity element. And in the previous video, we found that this is also equal to t squared. If you do a reflection about one axis and then you do that same reflection, you'd end up having what you started with. So that's t squared. And then you have t. T is a vertical reflection. TR is a reflection followed by a rotation. That's what TR means. And then TR squared means a reflection followed by a 240 degrees anticlockwise rotation. That is what TR squared is. So I did a reflection of a triangle, that's T, in the previous video. Now in this video, I'm going to focus on the algebra of this dihedral group. My focus is on the algebra. Remember, for this to be a group, it must satisfy all the four properties that I've mentioned. So anything I do here would always satisfy those properties. Now, the first thing we're going to do is we're going to do T composed with R. I'm just going to get rid of the composition sign because it takes a lot of effort to write. So I can't keep writing T composed with R composed with T. But don't think of TR and T as multiplications. They are composition laws. Okay? So T composed with R composed with T. Let's start with this. This is equal to R squared. So what does this mean? Remember the closure property. If you do a composition of any of the elements in the set, it must always give you one of the elements in the set. So if we take T, you can see there, then we compose it with R, you can see it there, then we compose it with T again, you can see it there, we would get R squared, and you can see R squared is also in the set. This is what we're trying to prove right now. So I'm going to prove this using the techniques that we've developed earlier on in this series. We'll start with the left-hand side. Left-hand side. So we'll do T composed with R composed with T acting on some triangle. Let me say 1, 2, and 3. This is the triangle that we're starting with. So that will be equal to, first, we will do T. Remember, what is T? T is a reflection about the vertical axis. So 1 would stay the same, and then you would flip 2 and 3. So 3 would come here, and 2 would come here. I am done with T. I'm done with the reflection. Next, I will do a rotation. 120 degrees anti-clockwise. So what would that give me? So let's do a 120 degrees anti-clockwise. So 1 would come down to the position of the 3. So you have 1 there. 3 would come to the position of the 2. And then 2 would come to the position of the 1. What am I keep making these mistakes. So 3 there, sorry. You'd have 3 there, and then 2 would move up. I think this is correct now. 1 comes down, 3 comes there, 2 goes up. Okay, that's good. So I've done rotation, 120 degrees anti-clockwise. Next, we'll do a reflection again about the vertical axis. So you would keep this 2 fixed, and then you flip 1 and 3. So 3 here and then 1 here. This is what we ended with. Sorry about that. This is what we ended with. And this is what we started with. This is the left-hand side. The result of the left-hand side is this. Now let's do the right-hand side. R squared. So R squared acting on that triangle that we started with 1, 2, and 3. What is this going to give us? Remember, R squared means rotate the triangle twice. So this one will move 1, 2. 1, 2. So 1 will take the position of the 3. 3 will move 1, 1, 2. 3 will take the position of the 2. And then 2 would move what? 3 would take the position of the 2. And then 2 would move 1, 2. 2 would go up there. Can you see that these two triangles look exactly the same? Yes, they do. So T composed with R composed with T is equal to R squared. Closure property is satisfied. Next, let's do another one. Prove that T times R squared times T is equal to R. Let me write that down so you can see very well. You can pause the video and have a go, try it. What do you think the answer would be? So another example, I don't know if I should call this an exercise. It's an exercise for you to try. Pause the video, try it, and then come back when you're done. So prove that T times R squared times T, not times, sorry, composed with, it's a composition, it's not a multiplication. So T composed with R squared composed with T would give you R. Again, you can see that we've done these compositions and we still ended up with an element in the set. Closure property is again satisfied, right? So let's start with the left-hand side. Left-hand side. So T composed with R squared composed with T acting on some triangle. So 1, 2, and 3. This is our initial triangle. That's the identity element. Do nothing. So first, we will do a flip or a reflection. If you do a reflection on that triangle, it's same as keep this one. You're doing a vertical reflection. Keep that one in its position and then flip 2 and 3. So you have 3 here, you have 2 there. We're done with the vertical reflection. Next, we'll do R squared. Remember, R squared is a 240 degrees rotation anti-clockwise, or R squared means rotate the triangle anti-clockwise twice. So to do R squared, this one, so that would give this triangle here. 1 will move 1, 2. 1 would come here. 2 would move 1, 2. 2 would come here. 3 would move 1, 2. 3 will come up here. So we've done R squared. Next, we will do T, reflect. So doing the reflection, this is 3. You would keep 3 and then you flip 1 and 2. So 1 here, 2 here. We've done the reflection. This is our left-hand side. Left-hand side, this is what we get. Now let's do the right-hand side. R, acting on this triangle that we started with, 1, 2, and 3. This is going to be equal to rotate. Remember, R means rotate 120 degrees anti-clockwise. So this one would come down here. This 2 would come here. Then this 3 would go back up. Can you see that the right-hand side and the left-hand side are equal? Yes, they are equal. That means T composed with R squared composed with T again would give an element in the set. Again, the closure property is satisfied. One final one. Let's do one last one. So for the next one, we're going to prove that remember, t squared is the identity element, right? We're going to prove that r composed with t composed with r is equal to r. Let's prove this. Now, I'm not going to act it on the triangle. I am just going to use some of the composition laws that we've established before now. So let's start with the left-hand side again. So left-hand side. I'm going to take t squared and act it on that triangle. T squared multiply times r times t times r. This is equal to, remember, t squared is the identity element. I can do this because t squared multiplied times rtr doesn't change it. So, or t squared composed with rtr doesn't change the operation, right? So I can do that. Now, the next thing I would do is I would simplify this. T squared is same as t multiplied times t r t composed with r. Remember, earlier on today we did t composed with r composed with t, and what was the result? Can you remember? T composed with r composed with t, the result is r squared. So you have t composed with r squared composed with r. But earlier on again, we did r squared composed with r, isn't it? So r squared composed with r is equal to what? The identity element, isn't it? So r squared composed with r, that's r cubed, which is the identity element. So t multiplied times the identity element is t. Oh, so this is not r. This is actually t. Prove that r composed with t composed with r is equal to t. So you can see there, starting with the left-hand side, we end up with the right-hand side. And that is some algebra of group theory. In the next video, we're going to be looking at the symmetries of a square and the Cayley table. Okay, so I'll see you all in the next video. Have a wonderful day.